So when we do a fit trace now, we can choose as usual a point to fit a curve to, and if we put in some initial values, we'll like negative 32. Let's put in 0.05, 0.2, and those should work. So now we've got, maybe if we do that 0, let's try something. Let's try to get our initial guess a bit better. That's a much better fit. Okay, so each time you do that, it does another iteration of least squares in this case, but there's many different ways of optimizing in this case. So once we say OK, we've actually got the error values now, which is nice, from the covariance matrix, which is printed out with PyModel. So the first thing I want to show you is MCMC fitting. So basically this technique will randomly vary the parameters, and if the parameters improve, then they improve in terms of the error that between the model and the data is reduced. It will accept that change. But if it's not, then there's a random number that says that there is a probability that it will still take on that new value. So that means we can span a lot more parameter space and work out what the most likely solution is, or the most probable. So there's no unique parameter value. So there is different distributions we can choose, and these are what's called the priors, and so this is the distributions at which the sampler will choose the parameters from. So we can use our intuition on chemistry and on the physical processes going on in order to guide our fitting. So we'll set a lower bound to be 0.01, let's say 100 here. We're using a uniform distribution, which just takes a uniform distribution between two values. There's also a normal distribution, which takes a normal distribution about the fitted value, with this as its sigma value, and the Poisson takes the Poisson distribution about the fitted value. So let's put in some values here. We know that this is going to be positive. We know that this is going to be positive as well. Let's say 0.5. We know this is going to be, let's say, negative 5 to 5, and let's say this is negative 0.01 to 0.01. So this here tells us the number of iterations that the sampler will go through, and this tells us the burn-in time, and I'll explain that when we run the simulation. So now if we press run, we see in the command window that we have this progress bar, which tells us how quickly this is going. So basically it's now randomly fluctuating the parameters and choosing the next value according to the criteria which is set by the MCMC, which stands for Markov Chain Monte Carlo. So what it prints out are the plots of the changing parameter value with iterations, gives you a distribution of a histogram of those values, and it gives you a autocorrelation plot. So basically what this shows us is that there is a stable distribution for A1, a stable distribution for, well, this isn't very well defined, this parameter, as you can see, which is kind of expected because that full width half max of that Gaussian can change quite substantially. Here's our Y0, here's our mu, here's our tau, so you can see there, that's this is how well defined it is, and I'm getting a summary that will be printed out on the log file, which will be good. That will tell you the mean and also the standard deviations. So the best thing about this is that if you were to fit with two exponentials, then you actually wouldn't get a nice distribution. You wouldn't get a stable solution. So let's try that. So let us fit now with a double exponential. So the functions I'm fitting with is basically an exponential convoluted in with a Gaussian, and so what I'll do is I'll set this to be about 3, this to be about 37, that to be about 0.05, that to be about 0.04, that's right. So let's fit that model. So that's good. We have got, we are thinking about possibly fitting this region here with a little bit of a faster decay. If we hold down Control, we can zoom in on that. So we'll see if we can do that anyway. So we go OK, and it prints out those parameters, and let's do an MCMC fit. Let me just do this quickly. So we'll choose about 5, maybe up to 10. So this here is, we're trying to look to see if there's any parameter around 3. And here we'll go from, say 5 all the way up to 100. So this is our 40, round about 41. And we know it's going to be positive, so it's good to do that. This is going to do that. Okay, so now let us run that. I probably won't do as many iterations because it'll save us some time. Oh, and I should say that the burn-in time is the number of iterations to discard in order for you to get a nice distribution. So you choose this value after you'd looked at the plots and said, okay, after 2,000 iterations, I've converged on a nice solution. So it's plotting those. Okay, so the first thing we see is that, I'll just pull it down, and let's have a look at these two tau values. Cool. So, the first thing you see is that tau 2 is quite well defined. It's got a distribution, but it's not a very stable solution, so it's jumping around a lot. Now, if you look at tau 1, we can see that there's definitely no distribution around here, and that the parameter can take on any value around this area pretty uniformly, maybe tending towards being a little bit further. So, I mean, this shows us that there is no actual stable solution at 3, and this was actually a minimum that the deterministic method found. So this is a really good way of working out whether you're overfitting something and whether that solution actually exists. So the next thing that is very exciting is global fitting, which I've just got working. So let's fit a single trace again with a single exponential. Put those values in again. let's fit that model. Alright, so we see that there has fitted nicely, and if I go OK, it prints those out. So now this here is the global fit. So let us choose some multiple traces. So I'm going to choose traces between just around about 600. So 55 traces were saved from 590 to 605. So there's 55 traces there, so let's do a global fit. So the global fit dialog has the parameters along the top, and this here lets you either fix a parameter or link the parameter. Now linking a parameter will link the value over all different fits, but it will vary all of the other, the unlinked parameters. So in this case it's very handy because if you look at the traces that come out of this, they have the same lifetime, however they have a different amplitude. So what we can do is we can link this parameter here, and we can globally minimize these for the specific wavelength. And this is implemented using PyModelFit, and basically I minimize the linked parameters using fmin, which is a function on SciPy's optimize. So we can set the number of iterations, the max iterations, and we will go fit. So currently it's going through different iterations. It's doing many. It's varying our tau1 value, and it's working out whether that gives us a globally minimized chi-squared value over all of the data. This works reasonably well and gives us a value of 38.325992228. Now I'm working currently on getting a better way of understanding the error involved in this, but these are comparable results to the previous global fitting we did. And hopefully I'll be able to do MCMC on the linked parameters, so I'll be able to vary those using a random MCMC routine, and that will allow me to work out, that will allow the distribution of those linked parameters to be better defined, so for working out models and whether those models do fit globally, it will be very useful for that.